I'm Kyle. I'm an engineer at Development Seed, and I'll be talking about GeoParquet and GeoArrow in deck.gl. So I want to go through a bit of motivation, some technical details, how to actually use this tech stack, and then some demos. The goal here is really, can we get simpler but faster rendering of large analytical vector data sets on the web? And so you're here, you probably know a bit about web maps. I think that there's really like three parts of a web map. Somehow you have to get the data into the browser, you have to manage the data in memory, and then eventually you have to render that data to the screen. So historically, you might take GeoJSON as the file format for getting data into the browser. You might store GeoJSON-like JavaScript objects in JavaScript, and you might pass that into like a GeoJSON layer in deck.gl as the three parts of this process. So that's pretty easy, but it's pretty slow, at least compared to what it can be. And so GeoJSON has a really big file size. It's really slow to write on the server and read on the client. And you can't read just part of the data set, even if you only care about the data in a specific location. And so the file is a bit slow. Managing that in memory is slow because there's a lot of memory overhead by storing each tiny coordinate array as a separate JavaScript object and a lot of garbage collector overhead. And if you want to do some processing on that data, where you want some of the processing to happen in a web worker instead of on the main thread, or inside of WebAssembly, you have to serialize that GeoJSON with a structured clone, which is really slow. It's basically like taking the GeoJSON, putting it back into a string, copying the string to the other thread, and then deserializing that string. And so that means that web workers have a lot less utility. And then deck.gl, to use the GPU, eventually has to copy the GeoJSON objects back into binary buffers because the GPU works in binary buffers. So text is slow. Is there some way that we could do this a lot faster? And so this is what I'm advocating for in this talk, where we can get data to the browser a lot faster using this new file format called GeoParquet. We can manage the data in memory in binary buffers as a table called GeoArrow and render it to screen with deck.gl's binary API. And so I think that GeoParquet is, in my opinion, the fastest way to move this analytical data because it's really efficiently compressed. You can read parts of the file without having to read the entire file, and really fast to read and write on both the server and the client. GeoArrow is the most efficient way to represent these geospatial data frames because you have everything in a binary buffer instead of small JavaScript objects. Because they're binary buffers, you can share the data between the main thread and a web worker completely free. You just change the ownership, it's called transferring, between the main thread and a web worker. And with WebAssembly, it has its own memory space, but it's a lot faster to move these binary buffers between the main thread, between JavaScript's memory and WebAssembly's memory. And it's free to go the other way. And then in deck.gl, we can copy this binary memory directly to the GPU. So let's start with GeoParquet. GeoParquet is based on Apache Parquet. And so Apache Parquet started in 2013 with a Hadoop project. And then it's a chunked columnar format. So if you look at the diagram on the right, you have the first horizontal structure is a row group. So every column's first, say, 100,000 rows maybe, will be stored in these contiguous column arrays where you have the first 100,000 rows for the first column, and then the first 100,000 rows for the next column, and so on. And so because this is columnar, the data within a column is much more similar than data across a row, which means that the compression in Parquet is extremely efficient. You get often like half the size of a CSV or a text file. And there's a lot of implementations that are pretty widely adopted. JavaScript, Python, C, Java, Rust, whatever you're using on the back end, you can get your data into Parquet pretty easily. So GeoParquet, it doesn't extend the Parquet format. It specifies a specific schema for how to store geometries inside of a Parquet file. And so recently, GeoParquet was released as a 1.0 specification, which stores geometries as a WKB encoding inside one of these columns. It's really nice that these files are readable by non-geospatial tools. So if you have a geospatial column, but you have attribute columns, you can use all those attribute columns in whatever you're already using for analysis of your non-spatial data. And there's a lot of increasing adoption here. There's, in the Python world, GeoPandas, GDAL and OGR have implemented support for this, which means that QGIS and other GDAL using tools are able to read and write this. And then in the future, we'll have spatial partitioning in addition for these files. That isn't quite part of the spec as in 1.0. And there's a really big community behind the GeoParquet initiative. So let's dive in a little bit more to GeoArrow. So I know this is a JavaScript conference, but I want to start way back in 2006 with the Python buffer protocol. And so there was this big issue in the Python land of different n-dimensional array libraries that each had their own C bindings to speed up something, or even Fortran bindings, but that it was really, really slow to work with all of these different systems that were using arrays because they had to serialize it into some format that the other library could use. And so the Python buffer protocol came along, and it enabled so much innovation because it allowed all of these scientific libraries in Python to use each other's data without knowing where that data is coming from, but also without any overhead. It's as fast as if the library were managing the memory itself. And so there's these tools like pandas, for example, that were built on top of NumPy memory. But then over time, it kind of hit the same problem, where you can see these screenshots on the right are from the Arrow documentation page, where you had all of these different systems that were using tabular data that you had to write specific methods for how to move the data between each system, where you have to write one method for every other library. And it's expensive to copy and convert this tabular data between languages. And so Arrow was designed as a language-independent way to share this memory across boundaries with these different tools. And so all of these tabular tools now can use originally implemented support for converting into Arrow and out of Arrow, and got the whole ecosystem for free. But then over time, all these new tools in the market today, so like Pandas version 2, Polars, Velix, DuckDB, et cetera, are all built on this memory format that Pandas and Polars and DuckDB can all use the same memory in Python without having to do any serialization. And here as an example, that data sharing with Apache Arrow is always constant time within a memory space. So in this example, this comes from a blog post where moving data between R and Python used to vary depending on the size of the data, but with Arrow, it's always virtually free to do that. This matters for R and Python, but that happens in the web too, with the main thread and web workers, and with WebAssembly and JavaScript, where it's really important to be able to move this data quickly. And so I would argue that we also have these same problems in the geospatial industry, where right now we have all of these different tools in lots of different languages that are using geospatial tabular data, but all have their own representations, and there's no fast way to move the data in between them. And so GeoArrow has a couple different really big possibilities. One, that it'll be heavily used on the back end because it will make it faster to interoperate between these different sources of data. But then also on the front end, by being able to be, as we'll see, really efficiently rendered in deck.gl. And so this is a young community, but it's been having wider adoption with integrations into GeoPandas, DuckDB Spatial, cuSpatial, which is a GPU spatial library. And so I think that there's a ton of potential for GeoArrow, not just on the server side, but also in JavaScript. And so this is a blog post I wrote where we have geometry operations efficiently rendered on GeoArrow memory, or efficiently operated on GeoArrow memory in WebAssembly. And that I think that in the future, there will be a ton of high-performance JavaScript applications that are really WebAssembly native, and that all the data operations are happening inside of WebAssembly, implemented in C or in C++ or in Rust. And the JavaScript is just used for rendering. And so this is an example of coloring buildings by their area, where that area computation and the reprojection is all happening in WebAssembly with a Rust library. And so how can we relate all of this to deck.gl? Well, I'd argue that deck.gl is incredibly fast. It can handle a ton of data, but that you have to get all that data into the browser if you want to be able to use it in deck.gl. And so the bandwidth is the limiting factor for large data. And because Parquet's compression is better than basically any other file format for this type of data, Parquet files are so much smaller. You can also only fetch the specific parts of a file that you care about with only specific columns and only specific regions once we have spatial partitioning in the specification. It's also really powerful to have the same data files used from the front end as you're using in the back end for your analytics. And so you can, instead of having one set of data that you do for analysis, that you work on for analysis, and a completely different copy of the data that you pass into the browser, where you have to kind of figure when is one of the copies out of date, how do you manage that? If you're using the same analytical format for both your analysis and the front end, that's extremely powerful and can minimize a lot of data copies. Now, deck.gl and GeoArrow are really powerful because deck.gl, it's a very low level and not fun to work with, but deck.gl has this binary API where you can pass these binary buffers into a layer. And so, for example, with the scatter plot layer, you can pass a buffer of XYZ coordinates, radius, a different radii per object, different colors per object, and so on. And that's really efficient because it doesn't use GeoJSON. deck.gl is able to copy these buffers directly onto the GPU. And so if we focus on how do we actually use this, first, get data into GeoParquet. A easy way to do this is with the OGR tool distributed with GDAL. It's a little bit messy. It'll be easier in a couple months, but this talk has a slightly different encoding in GeoParquet because WKB, you need something to parse that on the JavaScript side, and that'll probably come out in the next couple months. And so here in OGR for this demo, this is using geometry encoding equals GeoArrow, which is under discussion to be added to the spec in 1.1, but essentially stores these arrays of coordinates instead of encoding them into these binary WKB buffers. And then on the JavaScript side, we need a way to load and decode this Parquet data into a format that we can work with. And so I implemented Rust WebAssembly bindings on the Rust Parquet reader and writer. And so it's pretty straightforward to import this WebAssembly module, import the Apache Arrow library in JavaScript, fetch a buffer from some source, and parse that into a JavaScript Arrow table. And this also isn't a huge library. There's different ways to build it with different features, and it's under a megabyte for the WebAssembly bundle, which you'll quickly save back once you're using this really efficient Parquet file format. And so parsing this data set with 1 million buildings with the 7 million coordinates completed in 1.3 seconds inside of WebAssembly in Chrome. And so that's like orders of magnitude faster than you could parse a GeoJSON file in Chrome. And so this is what I was alluding to before. a new library that not only loads Parquet into Arrow, but also parses the WKB column into GeoArrow geometries. So this will be published soon. It's for technical details, it's not quite out yet. But hopefully in the next couple months, you'll just be able to have one line of code that takes whatever GeoParquet buffer you have and parses it into this really efficient arrow format. And then once you have this GeoArrow data in memory, the old way to do this was to use these low-level deck.gl, this low-level deck.gl API, where you manually have a data object that takes your table, takes a get position with a binary float64 array that you pass into this object. This works, but it's really confusing. It's easy to mess up, very low level. And so one thing that I've been working on the last month is a new JavaScript library to simplify this process for you. This is new, it literally released this week. And so this simplifies using the deck.gl binary API with this arrow and GeoArrow memory format. And so as deck.gl has a scatter plot layer, path layer, solid polygon layer, so this library has GeoArrow versions of each of those. And it makes it a lot easier. You get a GeoArrow table from somewhere, either parsed from Parquet or parsed from a GeoArrow file that if you don't want to use Parquet. And you just pass the geometry column into get position, and that under the hood manages the internal chunking of arrow, manages all of these different, manages validation so that you don't have to think about that. And so here, this is setting a constant red color for every object in this array. But if you have a table where you have pre-computed colors in your table, or you compute them on demand and store them in this arrow column, then here, the difference between these two slides is the get fill color here was a constant with a single RGBA value. And here, this is now a column within the table. And so each one of these values that's being displayed is a separate color per coordinate that is found based on the column. And so this is just passing this binary buffer directly into deck.gl. And so here, this is a demo of rendering 3.2 million points in deck.gl with this method. It hasn't actually been updated to use the new library that we just released, but you can check out this notebook and you'll be able to see all of these 3 million points rendered in deck.gl. So this is great. We love that we can do this in JavaScript, but like 99% of spatial data science happens in Python. And so is there some way that we could link the two and be able to get this amazing performance in JavaScript in Python as well? And so we are just releasing this this week as well, where this is a new Python package that works inside of Jupyter to take a geodata frame or an array of shapely objects and construct a deck.gl map that is based on these attributes. And it's really fast. So in this case, this is encoding all of the geometries from GeoPandas into deck.gl, and also having a different radius for every point and a different color for every point. And that happens in 2.5 seconds. So here, this is the full GIF. I run this cell. This cell from the Python side serializes this geodata frame to GeoArrow and then to GeoParquet. It passes that buffer from over the WebSocket from Python into JavaScript. And then on the JavaScript side, it parses the Parquet file into an arrow table, passes that to deck.gl, and is also computing colors for every point and the radius for every point, and is doing all of this in less than 3 seconds. And so this is way faster than any other library to date. And then once you've already created a map, you can update the rendering styles by only updating the buffer for that specific attribute. So here, we've already rendered the map once, and then we don't send the data buffer again to the front end. We only send the buffer of colors per point. And so it takes less than a second to update the color for every 3 million points in our Python notebook. As a performance comparison, I tried this with IPyLeaflet out of the box. It took 3.5 minutes and then crashed. PyDeck also took 2.5 minutes and then crashed. And then this took less than 3 seconds with this new library. So how is this so fast? It's because it's using this binary data pipeline that doesn't have text and doesn't have GeoJSON, doesn't have either Python objects or JavaScript objects at any step of the process. You take a geodata frame from GeoPandas, you serialize it to GeoArrow and GeoParquet, which is really fast, and this compressed buffer. You pass that binary buffer to JavaScript, you deserialize to GeoArrow, and you pass the GeoArrow to the GPU. This name comes from, it's a new binding to deck.gl. A deck is the part of a skateboard that you ride on. What's a fast geospatial skateboard? A lawn board. So yeah.
This is the reason this whole project, this one joke.
Yes, for that one joke. That's all we care about. Thank you to internet skateboarders for their training data for Dolly. And so some caveats here that this is new, like we literally published the 0.1 yesterday. The timings here, both for Longboard and for PyDeck and Leaflet, were on a local machine. If you're running this on a server like on Colab or on Binder or on some remote environment, you necessarily have to fetch the data from the Python environment to your browser to render. Now that'll be more efficient in this setup than ever before because this Parquet file, when I was testing it with this 3 million points, was like 50 megabytes and like 600 megabytes in GeoJSON. So this is a tiny fraction of what you used to have to transfer from cloud to your notebook. But it's still not going to be like 2 seconds when you have to download the data. There's a couple other things that we're working on, like showing tooltips and having multiple data layers in the same map. But go play around with this. This is on pip. Or alternatively, if you prefer JavaScript, check out this GeoArrow deck.gl layers, which is in the GeoArrow organization, and some other references with notebooks and to learn more about GeoParquet and GeoArrow. Maybe a little fast.